because it seems to indicate that something very special produced the initial conditions.
You say about the confidence level that you and your colleagues have about how this universe began.
When it comes to the confidence level, that's still very low. We can see observationally up to the first fraction of a second in our universe's existence. So up to that level, we have total confidence that we understand our universe, we know what happened. The big question is, where did that come from? What gave the energy of cosmic inflation? Was there anything before? Can we even ask the question of what was there before? And that brings about a lot of deep questions, not just about our universe, but about nature itself, because to have the right to ask the question what was there before, we have to accept that there is such a thing as time. The very word before does not have any meaning outside of the context of time. So is time emergent or is time fundamental? That's one other question related to the issue of the origins of the universe. When it comes to that origin, to that first moment of our universe's existence, we are willing to accept that we can study it by quantum theory. The reason being that the universe was tiny. It was one of the smallest objects one can imagine. So it makes sense to accept that that structure can be studied with quantum theoretical rules.
So right now, what is the feeling that the universe was in its the smallest it was, many orders of magnitude smaller than the smallest particle that exists?
So
it's a Planck scale. So what was it at that time?
At that time, we can think of the universe as a wave packet using the wave-particle duality. It's equivalently, we can also think of it as a quantum particle. But that tiny universe had a very high concentration of energy, and it was that energy that drove it into an explosion. The question becomes, but where did that energy come from? Why did we have to start that way? Sir Roger Penrose calculated that the probability to start with high energy inflation is ridiculously small. It's 10 to the power 10 to the power 123 times. So 10 to the power 10 and then another 123 zeros. But so that says that the chance of our universe starting the way it is seems ridiculously small, nearly zero. And that brings about a lot of paradoxes. So that makes scientists feel very uncomfortable, because it seems to indicate that something very special produced the initial conditions for our universe to come into being. On the other hand, it's hard to see how can we even ask the question, why did we start with this universe, without having a pool of many possible universes from which to start, from many possible initial conditions. We all agree there's nothing wrong with applying quantum mechanics at the beginning of the universe, because the universe is so small. If you apply quantum mechanics, what you find out is not just one solution, one wave function that will eventually become a universe, but a whole family of them. And there is no criteria in nature that says, oh no, you can keep only this one. So if you agree and accept that all the possible mathematical solutions one gets out of quantum mechanics have an existence or a right to exist similar to our universe, then we have to accept that there is a whole pool, ensemble of universes out there that underwent a similar evolution to ours. Starting from that wave packet initial state.
When people talk about the beginning, we have to ask, what does that mean? What is the beginning of the universe? If we assume that the geometry is classical, so we have a well-defined notion of time, you can talk about sequences of things in time, and you can try to extrapolate, this is what cosmology is about, the history of the universe backward in time.
Okay.
So how far can you go with that?
Right.
It depends on what you mean by what you think the limits are. If you're talking about the classical theory of general relativity, which is what we use in discussing the Big Bang, you can only go so far before the solutions, which represent the universe, develop singularities, infinities. And so what that really means is that the theory has broken down. Right. That is quite early, right? It's like 10 to the minus 43 seconds after the Big Bang. Yeah. And that's what most people are talking about when they talk about the beginning. Very early, back to the limit in which we can meaningfully describe a notion of time.
So that's way before inflation is supposed to be.
Way before inflation.
Yeah.
A lot of stuff works, right? Starting with very simple initial conditions, we can have a whole story about how the universe. So the question is, can you go further? Well, if you go further, you're in the realm of quantum mechanics, not certain space-time, but probability amplitudes for space-time. Then it depends on what the theory are. For example, you could make a quantum transition to a different space-time on the other side of this region where the classical physics doesn't apply. So you can go through quantum mechanically.
Sort of like magic.
It's a very simple thing. If you think of the decay of an atomic nucleus, it's sort of like bound inside the nucleus and it's bouncing around.
Yeah.
There's a sense in which you can describe classically what's going on inside the nucleus. But to get out, it has to tunnel through a barrier because it's confined by the nuclear forces. But it can tunnel quantum mechanically through the barrier and then behave classically on the other side. Mm. That's two regions of classicality connected by a quantum transition. Could the universe be like that? It could, right? Where we make a quantum transition to another universe on the other side.
So, but how does that help us understand what happened originally?
One possibility is another expansion on the other side.
So what would be the implications of that? Eternal expansion?
So it would expand on both ends, right? Right. Unfortunately, what also reverses is the arrow of time, according to our calculations. Right. So the arrow of time would point the other way. Their direction of time is going towards the direction of expansion. To signal us, they'd have to go backward in their time. Not possible. So they're effectively disjoint. So classical description, back to a very early stage, possible quantum description, not much help in explaining the universe that we have.
And so what is the fundamental implication of the Hartle-Hawking state?
Well, the most useful application are the prediction of the features of the universe that we see today coming out of the state, because we get probabilities for those different classical histories. And that's how you test the theory of the quantum wave function of the universe against the observations, not by having classical physics, but having an ensemble of possible classical universes.
Now, as an evangelical Christian, I would believe that God did create the whole universe, and I don't believe he just created the beginning and then let it run, but I do believe that he uses very elegant laws for creating the whole thing.
What do you mean by the whole thing? You mean the whole
history? Right, the entire block of
four-dimensional time.
The four-dimensional block of the universe, and of course in the quantum theory, this would be sort of like a whole Everett multiverse, a block of many different histories. So
that's a lot of work to do that.
Yes, well, I mean, I believe God is infinite and he can do that, but he seems to use very elegant laws. Now, these laws are his own invention. God has chosen to use very simple patterns for creating the future time from the past time. I mean, we can't because we're too puny, but if there was some supernatural angel who could fully understand it, if God told this angel exactly what the initial state was and the laws he was going to use, then the angel from those should be able to deduce what God is doing for the rest of it. Now, that doesn't mean that God didn't have free choice in doing it. It just means that God chose to use those particular laws and that particular initial state to evolve the universe.
And that would become completely deterministic, even though it is this vast ensemble of probabilistic universes the way we look at it.
Yes, I think in my own view, there's not really randomness in quantum theory, except there is the uncertainty, of course, as to which branch we right now are on. It's sort of like the same uncertainty as to the uncertainty of why my present experience is seeing the universe from this direction and you're seeing it from, from that direction. I think both are real, and I guess I am one that strongly believes that God created the entire universe from nothing, and in my view, that means he had to totally determine it.
Now, many quantum physicists who do believe in God would say that God created quantum physics to allow a flexibility or an uncertainty to play in the universe so that human interactions, human free will can be built into the system.
Yeah, I mean, Einstein said that God does not play dice, and I tend to go even further and say that God could not play dice. If by playing dice, I mean using something that gives random results that are not already determined by what God's doing. There's no random choices. There's nothing out there for God to bring in and use. This is all determined. But from our point of view, we can only see one outcome. So for us, the result looks random because we don't see the other parts. And God, if he had nothing other than himself to start with, I think that God doesn't even have the opportunity to be able to have randomness, that he had to create everything, and therefore I think he had to determine it all.